Hi everyone, welcome back to Coding with Bharat channel. So today we are going to start the new technique of the week, which is meet in the middle technique. So yeah, let's just directly jump on to one of the problems and then from there learn about the different concepts involved in this particular technique. So this is a problem I have taken from CSES since I felt that this problem was much better as a starter problem, which goes like this. Let's say you are given a simple array having n numbers, and what you want to do is you want to find out some subsets of this from this array such that they sum up to the value x. If we take an example like this, then you can see that okay, I want to make a sum of 5 and I have four numbers. So what I can do is I can make 3 plus 2 5, this 3 plus 2, or there could be a subset this 2 and 3, which is again 5, or there could be a subset this 2 and this 2 and 1. So 2 plus 2 4 plus 1 5. So out of all the subsets you need to find how many subsets have sum equal to the given x. Okay, so if you see what this problem actually talks about and try to think from absolute scratch that how would you solve such a problem, then the first idea that would come to your mind is to go ahead with something like a knapsack or a dynamic programming approach. So if you have been doing a bit of dynamic programming and you know knapsack, then what do we do in knapsack? We say that okay, we want to, or there is a famous subset sum problem as well, where exactly the problem is this: given an array, you find out number of subsets having sum equal to x. This is exactly what subset sum problem says. But the thing there is that we create a dynamic programming there, DP, of position comma sum. So all the positions possible into all the sums, and n into w is the time complexity. If you see here why dynamic programming doesn't work, anyways, if you don't know dynamic programming, no need to worry, you can still watch the actual meet in the middle technique. It's not a problem. I'm just for the people who know and for the people who are curious that why can't we use dynamic programming, I was just pointing out here that if you look at the constraints, the sum that we want to create can go up to 10 to the power 9. So the dp n into sum possible, that will go 40 into 10 to the power 9, and that's why we will not be able to create that array nor support this time complexity in totality. So because of these reasons, like dp approach fails here. But another point that you see here is that n is small, n is just 40. So yeah, these are the characteristics where you can start thinking about meet in the middle technique. That okay, the values are large, so a standard DP kind of solutions might not work. But simultaneously, the size of the array is small. So if you can modify your brute force to handle this much size, then you can probably go ahead with meet in the middle technique and improvise on it. So let's first talk about the absolute brute force to solve this particular problem, and then we'll go on and jump into the actual meet in the middle solution which optimizes on this brute force. Okay, cool. So first of all, given any particular array, if you want to generate all the subsets of it, the main idea behind that is you can use the take or leave approach. Take or leave. What is take or leave? At every element, you decide, do you want to keep it in your set or do you don't want to keep it in your set? So initially what I'll do, I'll have empty set. I'll make a decision for the first element 2. If I decide to take it, my set will now contain 2. If I decide to not take it, set will still be empty. Then from there, I'll make decision for 1. So similarly, if you look for 1, if I decide to take it, my set will kind of become 2 comma 1, and otherwise it will stay at 2. Here, if I decide to take it, the set will now have 1, otherwise it will be empty. So if you see what is actually happening, at each level, you are getting all the subsets till that position. So right now we have included 2 and 1 in our set. So we are getting all the 4 subset of just 2 and 1. Both 2 and 1, just 2, just 1 and empty. If we next include the next element which was 3, let's see what we will get. So we'll get 2, 1, 3 here, including all 3. Here we'll get 2, 1 because we are not including 3. Here again two options, either to include 3, we'll get 2, 3, or to not include 2. Here also 1, 3, just 3, and here also just 3 or empty. Oh, sorry, here there is just 1. Right. So if you actually see, again, you generate all the 8 subsets possible with 1, 2, and 3 in them. Right. So basically, the idea is that at every position you decide whether you want to take it or leave it and make a recursive call further for the remaining positions, right? And that is how we'll come up with a solution here. Okay. Here we are mostly interested in some of the elements, right? So what I can in fact do is, instead of maintaining the set, I'll just maintain the sum. That initially the sum is 0. If I decide to take 2, my sum will become 2. If I decide to leave 2, my sum will still remain 0. Then I'll make a same call for 1. If I decide to take the 1, my sum will become 3. Otherwise it will remain 2. Here also if I decide to take this 1, it will be 1. Otherwise it will be 0. So on and so forth. So in a way I can say that if I am at any given position and right now my sum is s, from there I'll make basically two recursive calls. First one being for next position and sum plus array of position. This is the take case when I decide to take the current element. Second case, position plus 1 but with just s. So you decide to leave, you don't decide to take, right? So this is how you can write a recursive function, that if you are at any position and having a sum s, you have two options now. Either you go to position plus 1 and find some s plus array position, or you go to f of position plus 1 and find the sum, like carry forward the sum equal to s only. Okay, cool. If we write this top down approach where we are passing down the sum, then when we reach the leaf nodes or when position becomes equal to n, we would be interested in knowing if we have acquired sum equal to our x or not, like the sum that we wanted. Have we got that sum or not? And based on that, we can do a plus plus in our answer. The problem with this is that the time complexity of this same approach is 2 to the power n. Why? At every position, you have two options, take or leave. So after first step, you made basically two calls. Next step, you made 2 to the power 2. Next step, 2 to the power 3. So at the end, you would have made 2 to the power n calls of doing O1 operations, right? So yeah, based on calculating the number of nodes in this tree, you will get the complexity as 2 to the power n. Okay. Now the point is 2 to the power 40 is a huge number. So if I simply go ahead on Google and search for this, so you'll see that okay, 2 to the power 40 goes up to 10 to the power 12, right? Which is kind of a lot. Meet in the middle can always and always work if you half this array, right? Divide into two parts. That is 2 to the power 20. And that we can see is within the range, right? So what is the total time? 1, 2, 3, 4, 5, 6. So 10 to the power 6. So what I will think about, instead of applying brute force on the entire array, we split the array into two parts, right? We split the array into two parts, apply the brute force on the first part, apply the brute force on the second part, then try to look at those combinations which occurs across. Okay, so let me take an example and then explain this idea. So let's say my array has 6 elements, 1, 1, 2, and let's say 2, 3, 4. And let's say I want to make sum equal to 7. Okay. Okay. Let's say we want to do this. So now you will see that, okay, let's say we divide the array into two parts. So we divide the array into two parts, this and this. Let's just look at the first part. In first part, we can run brute force. If we try to count the number of subsets having sum equal to 7, right? So what are the subsets of this 1, 1, 2? Just 1, again just 1, just 2, empty, then 1, 2, 1, 1, another 1, 2, and finally 1, 1, 2. So if you think about it, none of these sum up to 7. So 0. 0 is the answer if we take only the elements on the left half. Okay. Let's talk about the right half. Again, we will run brute force. What are the options of making sum 7? I can see a 3a plus 4. So 1. Okay. So we found the answer for only the left parts, only the right parts. Answer is 0 and 1. But the problem now is there could be some subsets having some elements from the left and some elements from the right that are being missed here. So if I talk about it, there could be a case where I take, let's say, this 4 and I take this 2 and 1, right? 4 plus 2, 6 plus 1, 7. Similarly, there could be a case where I take this 3 and I take this 2, 1, 1, right? So all these cases are actually missed out. Okay. So this is the most important part in meet in the middle technique, that okay, you realize brute force will not work for the entire array. Simultaneously, you realize brute force will work for half arrays. Now you have to find a way to combine those answers and quickly calculate the results which could be on both the sides, right? So this is an example of subset. I'll at the end also try to take an example of subarray also, where this kind of technique can definitely occur. If I take from the left side a sum equal to just 1, right? And in total I want to make sum equal to 7. So from the right side, what sum would I need? 7 minus 1, that is 6. So there are two ways, two sets here that make sum as 1. For any of these two sets, I can combine it with the one set here, which makes the sum equal to 6. What is that set? 4 and 2. 4 plus 2 is 6. So actually, if you think about it, I'll get two possible answers, right? Two possible answers. Which are those two possible answers? This one and this 2 and 4, or this one and these 2 and 4. So two possible answers in total of making sum 7 if I take 1 from the left and 6 from the right. Similarly, you can make computations of, okay, 2 from the left. That means we want to make 5 from the right. So if I want to make 2 from the left, I have what all options? I can take 1, 1, or I can take just 2. So two options again. So 1, 1 is one option, 2 is another option. So two options. Then we want to make 5 on the right side. So 5 on the right side, there's only one option, 3 and 2. So this, right? Let's say if there was another 1 here, then what we would have said, okay, there is 1, 1 and 2, two options on the left. On the right side also, we have 4, 1. 4, 1 is 5 and 3 plus 2, which is also 5. So two options. So we would have done 2 into 2, 4. Why? For every option on the left, we can match it with every other option on right. So you multiply. Okay. So in a way, what I can say is, if I store, if I calculate all the subsets on the left side and store it in something like a frequency map. So let's do that. So let's keep this 1 for now. I'll try to keep it and generate the frequency map. So let's generate the frequency map. Okay. Empty array, sum is 0. So there is one subset with sum 0. Okay. There are two subsets, single one, having sum 1. Let's talk about 2. We have 1, 1 and we have 2. So 2, subsets having this sum. Then to make sum 3, we have 2, 1 and the other 2, 1 also. So two options. Lastly, for making sum 4, we have one option. So we can count also 2 plus 2, 4 plus 2, 6 plus 1, 7 plus 1, 8. So this is the frequency map that okay, this sum I can get in these many number of ways. So this is the map on the right side and we have the map on the left side as well. Now what we can do, we can try to do matching. That okay, if I take 0 sum from here and I want to make 7, let's say k is 7 that I want to make. So I'll have to pick 7 from here. So 1 into 2, that is 2 cases. Plus, if I take 1 only from the left side, then I need to take 6 from here. So 2 into 2, 4 cases. Again 2 from here, so 5 from here. So 2 into 2, again 4 cases. 3 from here, 4 from here. So again 2 into 2, 4 cases. 4 from here and 3 from here. So 2 into 1, 2 cases. So 12 plus 2, 14 plus 2, 16. So 16 total cases that you can count also. You will definitely get the answer as 16. So that is the idea of meet in the middle. That your brute force, if you cannot work it out for the entire array, split the array into two parts, calculate those brute force on the two parts, and then combine the answer somehow. Okay. Very different from divide and conquer. Divide and conquer technique keeps on dividing further. Like you divide into two parts and those two parts get further divided. Then those two parts get further divided till you have trivial cases like single element or two elements, right? Like we do in merge sort. Here, it's not divide and conquer. You just do that once. You split it once, calculate the results and combine. Because splitting it more than once then will make the problem very complex. If it was not two maps but four maps, then the complexity would not have been possible to be reduced like this. If there were four maps that you needed to combine to get some x, then you would again need loops to get that sorted, right? So yeah, minor difference between divide and conquer versus meet in the middle. Divide and conquer keeps on dividing till trivial case and then combines. Meet in the middle, divide it once, do brute force on both halves, and then combine those results once only in quicker complexity. Okay. Let's also look at the code for it. So first thing that I've done, I've taken my n and x, so n or x, like both of them. Then I created a vector, took the elements and pushed them into the vector and called find result. So this was all input and then we called this find result. So in find result, what I'm doing is I am creating two maps which will store frequency for both the halves. So I am creating first unordered map frequency 1 and calling the function from 0 to n by 2 minus 1. Similarly, creating a frequency 2 and calling the function for n by 2 to n minus 1. So dividing the array into two halves, calling find sum for the left, calling find sum for the right. Okay. Let me also talk about this reserve that we are doing. So with maps, the thing is that if you don't know how many keys, how many values are going to be there, then how map functions, it tries to find the optimal hash value, right, to avoid collisions. But since ultimately collisions can happen, so then map what it tries to do, it tries to resolve it or rehash it or move the things around. So that is why unordered map, although the amortized complexity is O1, sometimes what can happen is there could be a lot of collisions and we can result into problems. So therefore, if you already know how many unique keys you are going to have or how much memory your map is going to require, you can reserve that memory in the beginning so that you already tell the map that okay, these many values we are going to deal with. And with that idea, the map can optimize the hash function and keep the elements separate and avoid collisions. So that is what I've done here. This step, I know that 40 is the maximum size of the array. That means in one half there would be 20 elements. And 20 elements, I know brute force will run 2 to the power 20 times. So at max, you would have 2 to the power 20 values in my map. So I've already reserved 2 to the power 20 space for my first map also and for my second map also. Removing this, it was giving TLE. So you can also try submitting it without this. Most likely it will get TLE. Okay. So yeah, basically building the two maps. I'll go to the find sum function, which is the recursive function. But before that, let's see answer calculation. So once I have those frequency map for both the parts, then for each frequency value in the first, I need to find the corresponding value in the second and multiply and add it to the answer. So I've declared my answer as 0. I go over the first map. Then I find out what is the frequency I need in the second map, right? So what the frequency? What is the value that I need in the second map? That is the total sum that I want minus the key of the first map. The key of the first map is the sum that I'm using for the from the first half. Okay. Then what I do, I try to see, okay, is this second value, the pair that I want to find, there in frequency 2 or not? If it is there, then I multiply value in frequency 1 into value in frequency 2 and add it into the answer. So the exact thing that we were doing, take frequency of 0 from, or take any frequency of y from first half, x minus y from second half, and multiply those and add it to the answer. Okay, let's look at find sum function quickly now. So find sum function, what it does, it takes the values from this L to R and tries to generate all the sums and put them into the map. So I have this unordered map. I have the sum so far that I'm passing down from the top, like I talked about it, and I have my x, right? So this x I have kept to remove all those branches where the sum already has gone beyond x. So the numbers in the array are just positive. So let's say if we wanted to make sum equal to 5 and the sum has already become 7, then there is no point in taking more elements to it, right? So that is why I have kept this x here to, like, if the sum so far has already become greater than x, we can directly exit from there. Okay, so let's look at the code. So I've said that, as I said, if sum so far, the sum that we have seen so far has already gone beyond x, simply return. We don't want to explore further options. Or if my L has become greater than R. So when will L become greater than R? When I have explored everything till the end and gone beyond, right? So if L has become greater than R, or I have got the sum as equal to x. So if the sum is less than or equal to x and we have breached L greater than R, then I'll do plus plus in the map for that sum and return. Okay. So if either the array is exhausted or the sum has come to x, if sum has become x, then again adding more elements doesn't make sense, right? So you'll have to leave everything. So either if sum has become equal to x or L has become greater than R, you simply put that sum into the map and return from there. Then you'll make two calls, one for leave and one for take. So this is the leave call where I say go to L plus 1, R, keep the map same, keep the sum same, keep X same, everything same. Just L becomes L plus 1. Second case is when I take this current element. I'll only try to take this current element if that doesn't exceed the sum, doesn't exceed X. So if in sum so far, if I add V of L, the current element, if that value still remains less than equal to X, then only I'll make this second call for L plus 1 R, going to the next step and adding the current value to the sum, right? So the take and leave recursion that we talked about. Okay, so this is the idea of, you can say, subset kind of questions using meet in the middle. As I said, I'll also talk about sub-array kind of questions, like how do we tackle those. Okay, before that, let's talk about time complexity. So time complexity for this, if you think about it, find sum is 2 to the power n by 2. That is 2 to the power 20 in a way, 2 to the power n by 2. Then for each value in the first frequency map, you are finding in the second, which is just O1. So again, this half is also just 2 to the power n by 2. So in total, if you think about it, the time complexity is 3 into 2 to the power 20, which is well within the limit of the questions. Right? Okay. As I said, let's talk about subarray. Like how do we deal with subarrays also in such scenarios? So in general, when we are dealing with subsets, you'll almost always see that okay, we are having some maps of values for the first half, maps of value for this from the second half, and we try to merge them. When we are dealing with subarrays, then the subarray that you are taking would either be entirely on the left side, like this, or entirely on the right side, like this, or it could contain the middle boundary. So if it contains the middle boundary, then it's kind of like one suffix from the first half and some prefix from the second half. So when we use meet in the middle in case of subarrays, then it becomes a question of prefix and suffix, because individually you calculate the results for both the halves and then you want to find the best suffix and best prefix and use that. Okay. This pattern we have also seen in one of the questions of in the Cadane part, right? Which talked about repeating the same array n number of times and then finding the maximum sum subarray. So that part was kind of similar to this technique that we are talking about right now. Cool then. So that sums up the technique in totality, the meet in the middle technique. We'll take one or two more questions on subsets majorly because subarrays anyways, like if n square works in one half, then it would work in totality as well. Like there could be very few questions pertaining to subsets where we probably multiply something multiple times, like we did in this Cadane's question, where we can actually see meet in the middle in the action. Most of the questions are based off of subsets problem as only. So we'll take up two more such problems in the coming days. Okay then everyone, see you guys tomorrow. Bye bye.